Good morning again. So we are now going to go into a more elaborate algorithm to build the convex hull of a set of points, which is called grand scan, a very great classic of computational geometry. So here we start from the same point of view as Jarvis March from the previous podcast. What we're doing, we first takes the points, here we have 8 points, and take as reference the point which is the lowest points of the set. We know that this point belongs to the convex hull. So we are going to create a global reference with respect to this point. Okay? And then here, if you look at the number I've associated to all the points, those numbers are corresponding to a specific ordering of the points. If you look here, for example, 1 and 2, and even 3, you look that those points are sorted with respect to the angle this points, the lines 0, 1 is making with the reference. So those points are all sorted with respect to angles they do with that reference system. Okay, so here we are going to use this thing to build the convex hull. First, we use a data structure called a stack here. We are going to stack the points, a certain number of points to stack the points, and the remaining points of the stack at the end of the algorithm will be the ordered set of points of the convex hull. So we start and we put 0. 0 belongs to the convex hull, and 1, 2 belongs to the convex hull because 1 is essentially the point that has the lowest angle. This would be the first point that would be chosen in Jarvis March. Okay? But now we are not going to do as bad as in the Jarvis March. We are going to proceed in order. We are going to add point 2. And this is not a final act. We always look at 3 successive points in the stack. It's 0, 1, 2. If 0, 1, 2 makes a clockwise turn, we remove the middle point. Okay? So what is a clockwise turn? It would mean that between 0, 1 and 2 we go clockwise. Here, look, we go counterclockwise. It's nice. So we conserve the 2. Okay? For now, this is not something which is definitive, as we'll see. So here, at this point, we say this could be a convex hull. There is no prevention for this set of points to be a convex hull. And so, because we only do counterclockwise turns, there's no clockwise turn in that order. So we put 3. Of course, when you go from 1, 2 to 3, you do a counterclockwise turn, so it's nice, no problem. Okay, we can add 3 in the stack without problem. Okay, 3 has its room in the stack at that point. Because 3 to 1, 1 to 3 does a counterclockwise turn. Let's move now to 4. Okay, so if you get 2, 3, 4, this is a clockwise turn. And we hate clockwise turn. We don't want to do anything with those clockwise turns. So when I put 4 into it, I just find out that, in fact, this set is doing a clockwise turn. So what do? I will remove the middle one. Okay? I'll remove it. And I'm going to check now if 4, 2, 1 do a clockwise turn. Let's look. Okay. 4, 2, 1 do a clockwise turn. Okay. Like that. Let's assume it's the case. it's at the limit, but let's assume it's the case. And then now we go and we put 5. Okay, and we look if 2, 4, 5. Okay, do a clockwise turn. It's the case. Yes, it's okay. Then we put 6. So if we put 6, what do we see? Oh, this is a clockwise turn. We don't want clockwise turn. So it means that, what do we do? Again, okay, we check if these things that does a clockwise turn, which is bad. And so what do we do? We just erase that one. Okay, which means that now those things are not there anymore. Okay, and we look if 6, 4, 2, okay, 2, 4, 6, do a clockwise turn. It's the case. Okay, so we continue, and then after I put 7, okay, and it's the last one. Okay, so this is my final convex L, and it's 7, 9 points to 0, and we have finally the convex L that has been computed in a pretty fancy way and smart way. So what is the actual computational time that we need for that? First, we have to sort. We have to sort those points, okay? We have to sort, and there is no way to sort points with a complexity which is lower than n log n. Okay, this is our n log n. But in the second round, we are only dealing with points once, so the next complexity is of the order of n. Okay, so which means that the overall complexity of this algorithm is dominated by the sort. Which means that this algorithm is of the order n log n, whatever the set of points you have. So of course, if you had this very specific set of points with 3 points like that, and many points inside, maybe Jarvis March would be better, but this Grams scan algorithm, in most of the cases, is a way better choice than the simple Jarvis March that we saw in the first video. So I'm stopping now, and I'm going to do a third video in a couple of minutes.